Okay, in this video we're going to look at identifying different functional groups and how you can do a qualitative test in a lab to identify them as well. So here's the first molecule. So looking at the functional group here, this is a ketone, and here a haloalkane. So ketone, that would react with 2,4-DNP, and it will give you the derivative, which is an orange precipitate. This functional group here, the haloalkane, you can react that with silver nitrate in ethanol, and you would get a white precipitate. The important thing is these are two separate functional groups, and as two separate functional groups they react independently of each other. So get another one. Okay, so here we've got carboxylic acid. That's carboxylic acid. So you could react the carboxylic acid with a carbonate, sodium carbonate for example, and you'd see bubbles. Here we've got an alkene. So the test for an alkene is to add bromine water and it would decolorize. Here we've got an aldehyde. So like ketones, aldehydes react with 2,4-DNP to give you an orange precipitate, but they also react with Tollens reagent as well, and they give you a silver mirror. So three separate functional groups there. Okay, lots of OHs here. This one is a primary alcohol. This one, because that carbon, sorry, this one's a secondary alcohol. This one is a tertiary alcohol because it's bonded to 3 other carbons. And this one is actually the whole thing, but it's a phenol. Watch out for that one, it comes up a lot. So phenols are weakly acidic, but they don't react with carbonates, but they are weakly acidic, so they react something like sodium hydroxide. And you can test for a phenol using bromine water. It decolorizes the bromine water, so it goes from orange to colours, and it also gives you a white precipitate. So that's how it's different to an alkene. This alcohol here, tertiary alcohol, can't be oxidized, so it won't react with potassium dichromate, but this one would. And it's got to be acidified, and this will go, a secondary alcohol will make a ketone, and the solution will go from orange to green. One thing on this, all three of these OH groups here would react with something like an acyl chloride to make an ester. Okay, so here we've got a halogenated benzene ring, and here we've got a haloalkane. Now, this delta positive carbon here attracts nucleophiles like OH minus and like water, and for that reason it would react with silver nitrate, giving you a white, in this case a cream precipitate, because it will release the bromide ion. This one here though, this carbon does not attract nucleophiles, so this chlorine would not be substituted. You wouldn't get a precipitate from this chlorine here, because nucleophiles are generally negative, like OH minus. It's not going to be attracted to the benzene ring, which has got a high electron density. So got all sorts going on here. Carboxylic acid, haloalkane, aldehyde, alkene, secondary alcohol, ketone, and a phenol. So although this is one molecule, each functional group can react independently of the other. So this one will react with carbonates, give you an effervescence. This one is silver nitrate to give you a precipitate. This one is tollens and 2,4-DNP. And remember, it can also react with potassium dichromate. It can be oxidized further. Acidified potassium dichromate. Double bond, that's for bromine. Secondary alcohol, again potassium dichromate. It's ketone, 2,4-DNP. It wouldn't react with the tollens. And phenol, weakly acidic, doesn't react with a carbonate, but it would react with bromine differently to how this reacts with bromine. The alkene decolorizes the bromine, the phenol decolorizes the bromine and produces a white precipitate. So there you go. You can, when you get a problem like this, split it up into all different functional groups and think what does each one do, how does it react.